Potential energy is stored energy. It's energy that's stored in the geometry of a system. If we want to store some energy, we want to put some energy in. And that's a great way to look at potential energy. And to kick it off, gravitational potential energy. Suppose that we have a mass. We'll do this on planet Earth, so gravity is trying to pull it down. But let's take that mass and apply a force to it to lift it up through some distance. This distance is the displacement. You can call that delta y, and it's even convenient to think about the y-axis. Let this be y initial and this the y final. So the delta y is the y final minus the y initial. But we're applying a force to lift it up, and this force is doing some work. Work is the force times the displacement times the cosine of the angle. But here the direction of the force and the direction of the displacement are the same. The work should be simply the strength of the force times the displacement. However, and this cheats just a little bit, in essence, the minimal applied force that we need to lift the object through that distance just has to be sufficient to overcome the weight of the object. So the work that's done is that force, but it's the weight, or mg, and times delta y. Or this is going to be mg y final minus mg y initial. And the amount of work that's being done, it's putting some energy into the system, and this is the change in the gravitational potential energy of the system. So the change in the gravitational potential energy is equal to this work that's done by the applied force, is going to equal the mgy final minus mgy initial. And with these terms being similar in form, it seems reasonable to give them a special name, kind of like we did with kinetic energy in a chapter or a section or two back. But this one is just going to be, well, if this is the change in the potential energy, then it seems reasonable to call the gravitational potential energy itself mgy. And that's the potential energy of an object in a gravitational field due to the gravity. Does turn out, just by the way, if gravity is a conservative force, then the amount of work that's done in moving the object from one position to another, it doesn't depend on the path. Since the gravitational potential energy here is based only on the height of the object, we can even do a little bit better. The amount of energy that's stored by that force depends only on only on the initial and the final height of the object. If we move the object from one point to another and take that path, or from this height to the above height, taking that path, or regardless of the path that's taken, the amount of energy that's being stored in the system is the same, and it's just going to be that the change in the potential energy is given as above. So from one height to another, as opposed to one specific point to another, may be a good comment to make. It's also said that potential energy is an energy that has the potential to do some work. If we take an object and drop it, so here's an object, drop it, it's going to start falling. In fact, it's going to accelerate downwards, and by the time it gets down, and if it's free fall, there's a free fall acceleration, And by the time it gets down here, it's moving pretty fast. So it has a final speed, but that also means it has kinetic energy as it goes down there. If it's dropped up here, it has gravitational potential energy. And as the object falls from the one level to another, and as it picks up speed, what we have is that gravitational potential energy is converted into kinetic energy. And then by the time the object picks up speed, if that were to hit something, it could move it and do work on it. And that goes along with the idea that a potential energy means that it has the potential to do some work. Where the potential energy becomes very useful in conjunction with the kinetic energy is in looking at the conservation of energy. Conservation of energy, conserved quantity, simply does not change over time. If I look at the total energy of a system at one time, it should be exactly the same as the total energy of the system at any other time, as long as I'm not letting energy escape from the system or some outside energy come into the system. I have to do the bookkeeping correctly, keep an eye on all the energy that's in the system. In particular, the initial energy, if we want to think in terms of an experiment, the initial energy is going to equal the final energy. However, the full conservation of energy can involve heat energy or thermal energy. It can involve light energy, sound energy. There are other energies that are possible, chemical energy. And that's beyond what we want to grapple with right now. We want to focus instead on just mechanical energy. And the word mechanical is going to mean simply kinetic energy and any potential energies that are present. So if a system has thermal energy involved, it's really not a mechanical system. Nevertheless, if the amount of other energies is very small, it may be approximately a mechanical system, and then we may just treat it as being mechanical to that approximation. And if that's the case, the conservation of energy can be converted into the conservation of mechanical energy. But the big overriding concept is conservation of energy. Conservation of mechanical energy only applies if the system itself is truly mechanical. And then we could say, well, the mechanical energy initial equals the mechanical energy final. If the mechanical energy is composed of, or if the system is one object in motion, we'd have the kinetic energy and its initial value, and we'd have the kinetic energy and its final value. If there's a potential energy involved, then we'd also have the initial potential energy, and we'd also have the final potential energy. So in essence, we want to take all the energies that are involved, sum them together to get the total initial energy, sum them together to get the total final energy, mechanical energy in this case, and that can lead to a very useful equation which shows up in the examples that relate to this. So that section was a little bit long, but I hope it hasn't been too dreadful to listen. Thank you very much.